Thanks for tuning into this Revision Zone Maths video. In this video, we'll be looking at examples of the chain rule. So let's take a look at the first question we have as an example. So the function we're dealing with is y equals x plus 1 all to the power 4. Now we've already seen this function differentiated in two different ways, no less. One was just by expanding out the power using the binomial expansion, or indeed directly expanding this out and then differentiating each term. And the second time was when we used the product rule to be able to differentiate this. Okay, but now hopefully you'll see this is so much easier to do with the chain rule. So let me say let u equals x plus 1. Then our function y equals x plus 1 to the 4 actually just becomes u to the power 4, right? So going to the chain rule in Leibniz notation, if I want dy dx, then since my intermediate variable is actually u, I want to go to a derivative of y with respect to u, and then I want to multiply that by a derivative of u with respect to x. And of course, this is our chain, where to go from y to x, I go from y to u, and then from u to x. So let's write this down. Well, I've got my u, so I can just say my du by dx is obvious. It's just going to be 1 because x plus 1 differentiates to just give me 1. And I've got my y as a function of u, so I can say my dy by du differentiates just to give me 4u to the 3, right? By standard rules for differentiating polynomials. So now I go and I stick these things back into my chain rule formula. So my dy by du is of course 4u cubed, sorry, and my du by dx is just 1. But of course I want the function written out in terms of x, so I'm going to go and replace what my description of u is. U is x plus 1, okay? So I'm going to get x plus 1 cubed. And here we go. So we've managed to figure out the derivative in this case fairly easily. It is worth making a quick point at this stage, which is it's generally a lot easier, people find, when they use the chain rule in the Leibniz form. So for the remainder of this video, we are going to be only using that form. So example 2, we have the function y equals e to the power x squared plus 2x. So already we see that the complexity of this function is quite high. We wouldn't be able to differentiate this by sort of other methods that we know quite easily. So we're going to use the chain rule again for this. And because we have a function of a function, because the exponential is a function and the x squared plus 2x is a function, then the idea is, provided I can just differentiate the exponential by itself, and the x squared plus 2x by itself, I should be able to write down the derivative for the entire function. Okay, so let's see that. So I'll again say let u equals x squared plus 2x. Well, then that tells us my y is actually e to the u, and we write down the statement of our chain rule. So let me just say that here, which says if I want to differentiate y with respect to x, I can actually differentiate y with respect to u, and then I can just work out the derivative of u with respect to x and multiply the two to be able to work out the derivative I was actually after. So again, the whole point of this is that our function y with respect to u, or y written in terms of u, is actually a lot easier. So dy by du is actually just going to be e to the u, and of course u is x squared plus 2x. So du by dx is actually going to give me 2x plus 2. So now I've just got to go back to the statement of the chain rule, and I've basically have to substitute things in. So dy by du is e to the u. So the first term I'm going to have is e to the u, and then my second term is going to be du by dx, which is going to be 2x plus 2. So I'm going to just say 2x plus 2. Of course, I need brackets here because the whole thing is being multiplied. So the only thing worth doing here is perhaps replacing the description in terms of u to something in terms of x, because we want our derivative written out in terms of x. So I can say, making a bit of room, dy by dx is actually 2x plus 2 e to the power, and now we replace whatever our u was in terms of x. So we say x squared plus 2x. Okay, so the best thing we can do maybe at this stage is tidy it up a little bit by factorizing out the 2, But otherwise, this is basically done, right? So we can just rewrite this. And we've managed to differentiate quite a complicated looking function fairly straightforwardly. Just to make a quick remark here, if we actually wanted to check the solution here, we are actually going to struggle. So even if I actually tried to manipulate my e to the x squared plus 2x to say, well, let me expand it out to say e to the x squared times my e to the 2x, and maybe I can use the product rule. Okay, but the problem is we don't know how to differentiate e to the x squared. Perhaps what we can say is not easy to check solution directly. And again, every time we have a statement like that, what that tells us is there's a real need for the rule that we've actually used, because if we did not have that rule, we wouldn't be able to do the derivative in the first place. Okay, so let's move on to the next example. So in example 3, the function we want to differentiate is y equals sine to the power of 4x. So let's jump straight in. Again, we want to use the chain rule. So I'm going to rewrite this as sine x all to the power 4x. Of course, this means the exact same thing, but once it's written in this form, I can see that one of the functions I've got is sine x, and the other function is taking something to the power 4. Okay, so let me say that. So let me say let u equals sine x, but when u actually is sine x, then y actually becomes u to the power 4. So here, again, we need to use the chain rule to be able to differentiate y with respect to x. And the chain rule says dy by dx is dy by du times by du by dx. Okay, so we're going to need to work out the derivative of u and the derivative of y. So u equals sine x as we have up there. That tells me that the derivative of u with respect to x, because we know sine differentiates to give us cos, is actually cosine, and since y equals u to the 4, that's just a polynomial in u, then when I differentiate it, that's just a standard sort of thing. It's going to give me 4u to the 3. So I go back to the statement of my chain rule and I say, well, what's my dy by du? My dy by du is 4u cubed. So I write that down, 4u cubed. And then what's my du by dx? My du by dx is cos x. So I write that down. But of course, the thing is that the answer we have so far here is in terms of both u and x, but u is a function of x, so we want to write it down perfectly in terms of x. So we say dy by dx is equal to 4 sine x cubed cos x. Okay, that's basically the answer, but we can simplify it somewhat. So we can rewrite it as 4 cos u sine cubed x, sorry, which is the more conventional way of writing this. So we have our derivative. So perhaps the only point worth mentioning is a quick remark, which is we have seen this before, and we got the exact same answer. So see video on product rule examples, right? For a check. So example 4, we have an even more complicated looking function. In the last example, we did sine to the power 4x. Now we have e to the power of sine to the power 4x. So let's work out a solution using the chain rule again. So we're going to say let u equals sine to the power 4x. That way, that tells us that y is actually equal to e to the u. And we've got to be very careful in what we're doing here, because whenever we set u to something, we better be able to differentiate it. Because if we can't differentiate that u as a function of x, then we can't really apply the chain rule. But in this case, because we've done the example just previously, we know how to differentiate sine to the power 4x. So we can just go to the chain rule. So we say chain rule, and we know that to get y as a function of x in terms of a differentiation, so dy by dx, we have to write down dy by du and then multiply that by du by dx, okay? But since my y is actually e to the u, then differentiating y with respect to u is easy. We just get e to the u. That's how exponentials are. But my u is sine to the power of 4x. Now, in the previous example, we did this from scratch. But of course now, since we've seen that example, we know what the answer is going to be. It's just going to be 4 sine cubed x cos x. Okay, you can go back and just confirm this if you prefer. So now that we actually have this, we can put that in the formula. So we can say dy by du is just e to the u, and du by dx is just 4 sine cubed cos x. So I'm going to multiply by 4 sine cubed x cos x, right? So perhaps I should put these brackets there. So once we've got that, the only thing that actually remains is being able to write this in a form that's completely in terms of x. So all I have to do is go replace this u with the definition of u that we actually made earlier, right? So I can say that tells me that dy by dx is actually equal to, just to tidy this up, it's going to be 4 cos x sine cubed x and then e to the power of sine to the 4x. Okay, so we've managed to work out the derivative of this nasty looking function. So in example 5, we have a function which we wouldn't actually be able to differentiate easily otherwise without the chain rule, because if we take a closer look, we've got 2x squared plus a half e to the 4x in brackets, and then the whole thing is to the power 3 over 2. So we can't easily expand this by expanding brackets, nor can we sort of get easy terms to be able to do this. We might get away with it by using the product rule maybe, but as you'll see, this is so much easier using the chain rule. So again, we want to work in Leibniz notation, so we're going to say let u equals everything on the inside of the bracket, right? Because we can differentiate that alone by itself. So let's make that to be u. So it's going to be 2x squared plus a half e to the 4x. Well, that tells me that y is actually equal to u to the power 3 over 2. And that's reassuring because we can definitely differentiate this y in terms of u, and we can differentiate this u in terms of x. So we should be able to use our trusted chain rule, which tells us that if we want to differentiate y with respect to x, I don't know why I wrote down u, so with respect to x, then what we do is we differentiate y with respect to u, and we differentiate u with respect to x, and we multiply them. Okay, so let's work out each of these derivatives that we're going to need, the dy by du and the du by dx. Well, the dy by du, since y is actually equal to u to the 3 over 2, then that tells me, because that's a standard polynomial type thing, that when I differentiate y with respect to u, I get 3 over 2 u to the half. Okay, that's fairly straightforward. And u, obviously, in our case, is 2x squared plus a half e to the 4x, then I differentiate this by differentiating each term. The first is just polynomial type, so I'm going to get 4x because that's the derivative of 2x squared. And the second term is a standard exponential, so I'm just going to get a half, which is going to come along for the right, times by 4e to the 4x. So perhaps it's worth simplifying this to say it's going to be 4x plus 2e to the 4x. Okay, so now that we actually have a description for both dy by du and du by dx, I should make this clear. I don't know why I have an x there. It should be a u. Okay, so dy by du and du by dx, then we can put them back in. Now perhaps it might be easier at this stage to come here and basically replace the u already, because we're going to have to replace it later, so we might do it now. What do we know u is? Well, u, we have it here, so we can just write that in. So u is going to be 2x squared plus a half e to the 4x, and obviously I have the power of a half, so I've got to put that in. So I actually have that. So once we have this, I can now, maybe it's better to write it down at the bottom of the screen here. It's better to just use that directly and just to write down the answer here. Okay, so my dy by du is going to be 3 over 2, 2x squared plus a half e to the 4x to the half, and then we're going to times that by du by dx, which is 4x plus 2x, not 2x, sorry, 2e to the 4x, and there we have it. So it's just worth tidying this up maybe, and then we're basically done. So we see that there is a 2 here, because 2 times 2 is 4, and there's a 2 there, and there's a 2 in the denominator. So maybe we can take a 2 out overall to say it's going to be 3 over 2 times by 2 times by 2x plus e to the 4x, and then it's going to be 2x squared plus a half e to the 4x, and the whole thing is to the power of a half, obviously. And since these 2's are going to cancel, then the final answer can simply just be written as 3 multiplied by 2x plus e to the 4x multiplied by 2x squared plus a half e to the 4x, and the whole thing then is to the power of a half. So we've worked out a derivative for our function y in this case. So we want to differentiate the function sine of cos of x. Again, we're going to use the chain rule, so we're going to use it in Leibniz notation. So let's say let u equals be cos x. So since u is cos x, then I can go and just replace wherever cos x is with u. Then I can say y equals sine of u, and obviously we can differentiate u with respect to x. That's easy. We can differentiate y with respect to u. That's also easy, so we can use the chain rule. So the chain rule would again tell us that dy by dx is dy by du times by du by dx. But since u is equal to cos x, then du by dx is equal to derivative of cos is minus sine, of course. And since y is equal to sine u, then dy by du is actually equal to cos, because the derivative of sine is cos, is equal to cos u. So once we have that, we put these back into dy by dx formula for the chain rule. Before we do that, it's probably worth rewriting the derivative of y with respect to u in terms of just slightly nicer function. So I replace the description of u. So since we know that u is actually equal to cos x, I'm going to replace the u by cos x. Okay? That way, when I put this back into the formula for chain rule, I don't have to do a lot of messing around. So I'm going to put it back into that formula. My dy by du is cos of u, and my du by dx is minus sine of x. Sorry, this should have been u, obviously. That's the whole reason why I changed the u to x earlier. So my dy by dx now turns out to be minus sine x multiplied by cos of x. And here we have it. So we have our derivative. So again, the chain rule just goes to show how powerful it is. Differentiating this sort of a function, we can't use the product or the quotient rule. We can't really use any of the rules that we know of. We'll have to go back to the definition of differentiation, which will be quite difficult to use. So having something as powerful as the chain rule means that we can differentiate this in a fairly easy way, as long as we just know how to differentiate simple things like cosines and sines. So I hope you really do appreciate the value that the chain rule brings. So example 7 is also a very interesting function. We've got cos x plus sin x all raised to the power 5 to be able to differentiate. And obviously this without the chain rule would be quite hard to do as well. So we're gonna use Leibniz notation. So we're going to say let u equals cos x plus sin x. So since we have that, then my y just becomes u to the power of 5. Okay? So the chain rule would tell me that actually the dy by dx is dy by du times by du by dx. So I need to work out from my u, I need to work out what du by dx is. Well, I can just differentiate sort of each term here. So the cos is going to differentiate to give me minus sine x, and the sine is going to differentiate to give me cos x. So I'm going to say plus cos x, and the the other term we've got to differentiate is y equals u to the 5. So when we differentiate this, we will just get dy by du obviously is going to be 5u to the 4. Okay, so at this stage, we turn to our chain rule and we just put things in. So we say the dy by dx is basically going to be dy by du, which is here. So I've got 5 u, which is obviously u to the 4 times by then du by dx, which is actually here. Okay, so I say minus sine x plus cos x, right? So obviously, as per the convention, we want to write down the answer only in terms of x. So we want to replace what we have as u as in terms of x, but we know what the relationship between u and x is. So if we go back and say it's going to be 5 times by the cos of x plus the sine of x all to the power 4 multiplied by, well, let's just tidy this up, swap the cos and sine around just to make it easier. So we have a positive term first. We have cos of x minus sine of x. And again, we've worked out a derivative, which otherwise would have been quite hard to work out. So let's have a slightly more involved application of the chain rule. So in this case, we're given the function cos squared x plus sine squared x, and we actually want to differentiate it. And what we're going to do is we're going to apply chain rule twice effectively, once to this function and once to that function, and then add up the answers because we know to differentiate the function y with respect to x, we've just got to differentiate this function with respect to x, and we've got to differentiate that function with respect to x. And since we can differentiate each one of those functions individually using the chain rule, then we can write the solution down. So let's say solution. So I'm going to just look at the cos squared x here, and we might look at, say, the sine squared x here, right? So let me say let y equals cos squared x. I should say the y in blue is not the same as the y with sort of defined above. I'm just doing this to be able to use the chain rule in a slightly easier way, symbolically speaking. So in this case, I can say take u to be equal to cos x, and then that tells me my y is actually u squared. So the chain rule is obviously dy by dx is equal to dy by du times by du by dx, but my u differentiates to give me the derivative of cos is minus sine, and the derivative of u squared, so dy by du in other words, is just 2x, 2u, sorry, shouldn't say x because the variable is u, so 2u. So now that we have this, I go back to sort of my description of chain rule, and I put that in. So I say, well, what's my dy by du? That's just 2u. So let's write that down. So 2u. And then what's my du by dx? Well, that's just minus sine x. So let's write that down. Minus sine x. And we want to write the u in terms of x, but we know u is just cos x. So we can write that down, and simplifying this would give me minus 2 sine x cos x. Yeah, so I've done all of that in sort of one step. So if we've managed to work out the derivative of cos squared using the chain rule, let's go back and perhaps we can write in green this time, and let's work out the derivative of sine squared. Let y equals sine squared x. So we're going to repeat the same sort of argument. I should clarify here that this y in green is not the same as the y in blue or the y in black. Again, I'm just saying this as a way of making the writing this down part slightly easier. So we're using familiar symbols as opposed to me just bringing in lots of new symbols. So we want to now take u to be, say, sine x, and then that tells me that y is again equal to u squared. So again, it's crystal clear, I'll emphasize that this u in green is not the same as this u in blue, right? For the same reasons I've given. So by chain rule, now I can say my dy by dx is going to be dy by du times by du by dx. So I need to work out my du by dx and my dy by du and du by dx. So I can go to my u and I can say, well, I can differentiate u with respect to x. That's really no problem. And the derivative of sine is obviously cosine. And we can also differentiate y with respect to u. And because u is y is u squared, then the dy by du is just 2u. So since we have that, we can put that back into our chain rule formula. And what we actually get is we get dy by du is equal to 2u times by du by dx, which is cos x, right? But as before, we want to write this out so that there's no u's in there. We want just sort of x's in there, but my u is precisely sine x. So when I put that in, what I actually get is I get 2 sine x cos x. So we've managed to work out the derivative of sine squared. So now what I want to do is I want to write down the derivative of, oops, let me not do it in green, let me do it in black. I want to write down the derivative of all of sort of dy by dx, right? But that's the same thing as me writing down the derivative of the first function and then the second function. But we know what the derivative of the first function is. We have that here. Okay, so it's going to be minus 2 sine x cos x. And the derivative of the second function is we have that here, which is going to be plus 2 sine x cos x. And of course, the two are going to cancel to just give me that the derivative is actually 0. And we shouldn't really be surprised by this. This is the remark. We know by the identity cos squared plus sine squared equals 1 that actually the function that I started with can just be rewritten as y equals 1. So y equals 1 was our function, right? And if I want to differentiate this function directly, then when I differentiate a constant function, we've already seen that we just get 0. So as it happens, we actually get the exact same answer in both cases. So let's give ourselves a tick and maybe move on to the next example. So let's take a look at example 9. This is what's called a meta example. In other words, it's an example that you can actually use to construct lots and lots of examples. So in this case, we have a function y, which is made by just taking some function f and raising it to some power, where the power can be any real number. And what we have to show is actually there's a formula for working out how to differentiate the function of the form we were given initially, right? So it doesn't matter what f is, we can always use this formula to be able to get this out for anything we'll see on the A-level syllabus. So let's use the chain rule to be able to do this. Since y equals f of x to the power n, we say take u to actually be equals to f of x, right? Then what do we have? Then we have y is equal to u to the n, okay? So now here's the point. So if we can differentiate this function, which we can because it's just a polynomial, because n is just a real number, right? So we can sort of differentiate things like that. And if we can differentiate that function, yes, for any function we'll see on the A-level syllabus, we can differentiate these set of functions. Then we can use the chain rule in this case, okay? We can completely go and use the chain rule formula, which would tell me that dy by dx is going to be dy by du times by du by dx. Okay, so well, what's my dy by du? Well, my dy by du is just equal to nu to the n minus 1 because it's a standard polynomial type thing. And then my du by dx, let me do it above here, is actually just the function f differentiated. Okay, so once we have that, I can go back and I can put both these things into my chain rule formula. So I can say my dy by dx actually is going to be nu to the n minus 1 times by f prime x. And of course, at this stage, we are done. The only thing I need to do is basically replace my u from being in terms of u to being actually in terms of x, which is above there. So I'm going to get n times by f of x, which is my u, and then the thing is going to be to the power n minus 1 and multiplied by f of x, obviously the derivative of. So we've managed to show that the formula works. So we've done the meta example. However, this is sort of an abstract thing. So let's see let's see as a remark something more concrete. So let's see more concretely, right? If f of x was actually say sine x, right, and n was actually 4, then y equals f of x n actually becomes sine x to the power 4, right? Which we've sort of seen repeatedly in this video, which obviously we would write as sine to the power 4x. And let's differentiate this now using the formula we have. So what do we want to do? We want to put the n down. Our n is 4, so we put the 4 down, right? Then we multiply. What do we multiply by? Well, we have a bracket and we put the f of x inside. So let's have a bracket and let's put the f of x inside. Well, my f of x is of course, given how we've sort of defined it, it's sine x. So I'm going to just put sine x in the brackets here. And then what happens to my power? Well, it comes down by 1. So let's reduce the power down by 1. It was 4, so now it has to be 3. And then I basically multiply whatever's left by f prime. But my f is sine, so f prime, in other words, the derivative of sine, is cosine, which actually gives me 4 sine cubed x cos x, okay, which is a result we've seen repeatedly. But now I hope you would agree that with this formula, especially if you've had a bit of practice using this formula, it's dead easy to just write these things down. So we're finally doing example 10, which is the last example for this video, and in this case, I thought it's probably worth looking at something a little bit more interesting. So what we're going to try and do is we're going to extend the chain rule formula. So far we've seen chains of with only sort of one variable in the middle of the chain. It's been u, but now we've got two variables, right? So if you want to go from y to x, so you want the derivative of y with respect to x, then one way of doing it is to go from y to u, and then to go from u to t, and then to go from t to x, right? And obviously you multiply the respective derivatives, and the answer you'll get is the same as the answer for y with respect to x. So let's see how that might actually be true. So we have to define a function. So say it's going to be f of g of, now this is what we've seen in the past, it's going to be f of g of x, but because the chain is longer here, we actually have a triple function. So we have f of g of h of x, right? So with that, I can say take maybe u to be g of h of x, and take t to be h of x. So since we have this, then what that tells me is basically that is u is equal to g of t, right? T is equal to h of x, and of course y is equal to f of u, right? So this is completely consistent with how I've defined my u. My u is all of this thing on the inside, so y just becomes a function of u, which I have there. Then my u is obviously all that thing on the inside, but the thing on the inside of the g can be taken to be t, so u becomes actually just g of t, and since t is the thing on the inside, I've just said that here, right? So once we have this, let me just write down by chain rule. So by chain rule, let me just write down what am I going to get if I have dy if I want dy by dt, say, right? Let me just say I don't care about dy by dx, I just want dy by dt. Well, by the chain rule that we already know, it's going to be dy by du times by du by dt. So that's effectively what we've seen so far. So that's our chain, and we're going from y to t, but we're going via u. Okay, so this is a tick. This is completely okay. Now that's just an equation. The thing I've got here, the chain rule equation. What I can now do is I can multiply both sides of the equation by the same thing, right? So let me now come to the same equation, and let me write that down. So dy by du times by du by dt. And let me do it in a different color maybe. Let me say I want to multiply the left-hand side by dt by dx, and I also want to multiply the right-hand side by dt by dx. This is completely allowed by sort of rules of algebra. But look, once I actually have this, right, I can't easily say what this thing on the right-hand side is, but I can say what this thing on the left-hand side is. Well, how can I say that? I just apply the chain rule again, right? So now I'm going from y to x, but I'm going via t. So I've actually got a chain rule description on the left-hand side. So what I do is I come here and say by chain rule, right? What I can actually say that dy by dx is the same thing as dy by dt times by dt by dx. Okay, so let me call now this statement star, but then I can use star and go back to the sort of above statement, the statement here, the entire line, and I can say I don't care about the right hand side. I know the left hand side is just dy by dx by star. Okay, so I'm just going to replace the left hand side by dy by dx using star, and I'm just going to rewrite the right hand side as dy by du times by du by dt times by dt by dx, right? But this is precisely the statement I actually wanted to show. The fact that we can take the chain rule and we can extend it, right? So the reason why we've had to actually extend the chain rule is because, let me perhaps write it in sort of maroon here, is because so this function, maybe I should call it sort of double star, right? The function is now not a simple composite function. So in other words, chain rule was initially seen in the context of a function, right? What we now have not a function of a function, right? But we now have a function of a function of a function. Okay, so we actually have a triple set of functions in there. So I should say this is really a type of meta example. So perhaps it's worth seeing something a little bit more concrete. Let me make some space and we can look at something a bit more concrete. So let's consider a concrete application of the above rule. So we might want to say look at a function which is sort of quite complicated. So say we define something like y equals e to the power of sine. Now, if I stick an x in there, that's just going to be a function of a function because that's my first function, that's my second function. But what I actually want is I want another function on the inside. So let me say write down another function on the inside like x squared plus e to the x, right? So that's a mighty function. So we want to differentiate differentiate this function. So how we're going to do this, we are just going to apply the chain rule, but in the form that we've actually got above there, right? So let me just say, so let u equals say sine of x squared plus e to the x, right? Well, that helps me because that tells me that I can just write my y as e to the u. So now y is just a very simple function in terms of u. But then my u is a function which is slightly complicated. I can then say let t actually be equal to x squared plus e to the u. But since I say my t is x squared plus e to the u, or I should say e to the x rather, I'm getting mixed up in my symbols. E to the x because I just want my t to be everything on the inside here. So that's everything on the inside. I just made it to be t. So then my u actually can just be written as sine of t, right? So I've done nothing there. I've just said all of that is t, so I can just say u is sine of t, which is what I have here. So now let's consider what's happening. So we've got an equation. We've got equation one. That's a very simple equation. We can differentiate that. We've got equation two. That's also a very simple equation. We can also differentiate that. And we've got equation three, and that's also a very simple equation, and we can differentiate that, right? So which means if I go to the statement here, dy by dx is equal to dy by du times by du by dt times by, that should have been dt by dx. Silly me, right? So I'm glad I actually looked at that. So let's just fix that in the right color. So t by dx, right? So the point being that since I can differentiate, since I can have that from first equation, I can have this the du by dt from my second equation, and I can have dt by dx from my third equation. I can actually use that version of the chain rule to just differentiate my function y with respect to x directly, right? So so maybe we would just do this. Let me for now just for clarity just write this down in sort of black. That's okay. So dy by du is actually going to be e to the u, and du by dt is actually going to be the derivative of sine. It's just cos, so it's just going to be that. And the third one is obviously, let's do it here. So dt by dx is going to be, well, I'm going to have to differentiate each term here. So x squared differentiated is 2x, and then e to the x differentiated is just e to the x, right? So I'm glad I did this in black, because what that then means is I can easily see my answers. So dy by dx is dy by du times by du by dt times by dt by dx. So now let's just put things in. So my dy by du is just there, so I'm just going to say e to the u. Okay, so e to the u, and then my du by dt is just here, so I'm just going to say times by cos t, and then finally I'm going to just say my dt by dx is just here, so I'm just going to write that down. So it's going to be 2x plus e to the x. Now the only thing we have to do is go back and just rewrite that u in terms of x and rewrite that t in terms of x. But we know what they are because the u isn't already in terms of x here, and the t is quite nicely to be written down in terms of x. So I can just come here and say, okay, well my u is sine of x squared plus e to the x. So that's my u gone, and my t is just x squared plus e to the x, and then the other thing just comes along for the right. It's just 2x plus e to the x. So we've been able to work out the derivative of something which is quite complicated, very complicated indeed, and we've actually used a sort of a higher order version of a chain rule to be able to work this out. So with that, I'd like to bring this video to an end. We hope you found this useful. If you did, please hit the like and subscribe buttons. Do let us know in the comment section what you would like to see more videos on. Thanks for watching, and we will see you in the next video.